dive right in. Today, we're going to stare down a mathematical monster, a problem that for centuries would have been considered completely and utterly unsolvable. So, what exactly are we up against? Just take a second to let that sink in. This is the beast we're trying to tame. It's an 18th degree polynomial with a whole mess of terms. The challenge? Find the value of x that makes this entire thing equal to 0. And we're not talking about a close guess here. We are hunting for the exact perfect answer. So you might be wondering, why is this considered so hard? Well, for a very long time, finding the precise roots of a polynomial this complex wasn't just difficult, it was thought to be fundamentally impossible in many cases. Let's dig into why that is. I mean, that's the whole ball game, right? How do you possibly untangle this web of numbers and exponents to find the one precise value that makes it all balance out to 0? It's not about getting close, it's about being perfect. To really appreciate the breakthrough we're about to see, you first have to understand the old ways of doing things. We need to look at the traditional tools mathematicians had and why they just don't cut it for a monster like this. Okay, this right here is the key difference. On one hand, you have approximation. Think of it like a blurry photo. You can make out the general shape, but you're missing all the crisp details. On the other hand, you have the exact symbolic solution. This is the high-resolution blueprint. It's flawless, it's precise, and for a mathematician, it's the holy grail. That's what we're after. For a long, long time, a famous idea called Abel's theorem basically told the math world, don't even bother trying to find a blueprint solution for most equations of the fifth degree or higher. It can't be done. It was like a giant stop sign. But as this quote from Mourad Sultan Ezouidi suggests, what if there's a way to just go around that stop sign completely? And that, right there, brings us to the secret key that unlocks our polynomial. This isn't about using the old tools better or trying to brute force our way through. Nope. This is about using a completely new tool, a whole new way of thinking about the problem. And this is it, Ezouidi's theorem. Now, it's really important to know this isn't some kind of magic wand. It's a structured, repeatable process. The theorem basically gives us a recipe, a recursive one, that lets us chop this giant, scary problem down into smaller, much more manageable bites. So, how does this recipe actually work? Let's get into the guts of this thing. We're going to focus on the core idea behind the calculation without getting totally lost in the weeds of the formulas themselves. So instead of trying to wrestle that huge equation to the ground directly, the theorem takes this really clever detour. It says, let's define 18 new values, these symbolic coefficients. And here's the cool part. It's like setting up a line of dominoes. The theorem tells you how to calculate the value of the first one. Then the value of the second domino depends on the first. The third depends on the second, and so on, all the way down the line. It's a chain reaction designed to uncover the equation's true DNA. This process involves a ton of calculation, knocking down each one of those dominoes from the first to the 18th. Now, you'd expect the results to be just as messy and complicated as the original equation, right? Well, what happens next is nothing short of amazing. And bam! Look at this. This is the power of the method. After that whole recursive domino chain, almost every single one of the new coefficients just collapses to 0. It vanishes. This is no accident. The process is specifically designed to cancel out all the complex noise, leaving behind only the handful of terms that really define what's going on. It turns out all that complexity was just hiding this incredibly simple signal. Okay, now for the grand finale. We've done the hard work, we've found that hidden simplicity. Let's see how this completely transforms our monster problem and finally gives us the answer we've been looking for. So here it is again, in all its terrifying glory. Remember all these crazy terms? Well, you're about to see them in a whole new light. Because all those other dominoes fell to 0, the theorem lets us rewrite the entire polynomial like this. That's it. The 19-term beast has been tamed into just 3 simple terms. It's the exact same equation, just seen through a much, much more powerful lens. And when we plug in those 2 values we found, the ones that didn't disappear, this is what we're left with. I mean, look at that. What looked absolutely impossible a few minutes ago now looks, well, it looks solvable. It's clean, it has a simple, elegant structure. And from this beautifully simple form, we can now finally derive the answer, that high-resolution blueprint we were after from the very beginning. And there it is. This is one of the 18 exact symbolic roots of that monster equation. Now look, the point isn't to try and punch this into a calculator. The real triumph is that this answer exists. It's a perfect, elegant expression built from symbols and radicals. No approximations, no rounding errors, just a beautiful, definitive answer to a seemingly impossible question. So let's just quickly retrace our steps. We started with a problem that looked absolutely hopeless. We saw how the old methods could only ever give us a blurry photo, an approximation. But then a new theorem gave us a step-by-step process, a recipe that peeled back all the layers of complexity, revealing a beautiful hidden simplicity. And that simplicity led us straight to the exact perfect solution. And that just leaves you with a really cool thought, doesn't it? This wasn't about more computing power or grinding through the problem. It was about finding a new perspective, a different key for a lock that everyone else thought was unpickable. It really makes you wonder what other impossible problems out there are just waiting for somebody to come along and find the right key.